So what I'll be discussing today is how COVID-19 epidemic mitigation is occurring through the use of different techniques of scientific machine learning. So I'll start by explaining what scientific machine learning is because it's kind of an emerging discipline. So I think that most people don't know much about scientific machine learning as a whole. So machine learning has led to many major advancements in recent years. And everyone really knows, you can probably pinpoint lots of different things that machine learning has led to, like natural language processing and image processing are now considered pretty much solved problems, right? But these techniques require a large amount of data. And with epidemics especially, or with a lot of medical problems, we don't have that kind of data until it's too late, right? So is there a way to kind of use the ideas of machine learning without making it so data hungry? This is the core problem of what people are trying to solve with scientific machine learning, because in a lot of scientific cases, if an experiment already costs a few $1 million, you can't do the Google scale of, oh, just get 300 billion data points and train a neural network. That's just infeasible, right? And so what we do here to understand where scientific machine learning comes from, let's take a step back and understand why these advancements in the machine learning started working, right? And the core idea is that convolutional neural networks are something that imposes a structural assumption on your data that should be satisfied and thus makes it easier to learn, right? So convolutional neural network, what it does is it basically takes these big squares and it makes them into small squares by doing a convolution operation. For example, the mean pool will just add or take the mean of all pixels nearby, right? So what this is doing is it's saying, well, you could have pixels over here influence pixels over here and all sorts of different interesting relationships. But what the convolutional neural network is going to do is assume that pixels that are nearby contain somewhat the same information, and so you can convolve down and you can utilize the information about how a picture is constructed to be able to get something that's easier to learn from. So using that spatial information really ended up being the key that was required to make image processing work well, right? So it's really, even though you want your machine learning to be as unstructured as possible, it's really structural assumptions that really make it generalize better and make it easier to learn. And so if we want to be able to use structure to be able to influence and improve our machine learning, we really have to ask the question, what is the structure of science, right? If we want to use the structure, well, we have to figure out what it is. And it turns out that, like if we look at an ecological example, what you see as the structure of science is you end up having interaction networks, you have differential equations, you have mechanisms, right? So when you write down a set of differential equations, you're not, what really is in there is not necessarily the equations. I mean, the equations are there, but what's truly there is a mechanistic model, right? The mechanistic model says the rate at which rabbits are going to be increasing, if everything was in isolation, would just be exponential growth. They would grow proportionally to the number of rabbits there currently are, but there's another mechanism in there, right? This mechanism is that rabbits get eaten by wolves, and then how do the wolves change over time? So the way these models are built up is they have mechanism, right? These can be phenomenological models, or they can be based on many more scientific experiments, right? So here's an example that I pulled from zebrafish hindbrain studies where, over time, thousands of experiments have really figured out how the chemical reactions are occurring within the zebrafish hindbrain, and that structure of what connects to what and the way that these connections are occurring ends up giving you these structural differential equations where there's no data set you can point to. There's no 3 billion point data set that says that those equations are correct. But we know from different isolated studies that this set of equations is representative of the system and is something that you can use to understand and predict how pieces of behaviors will happen in the zebrafish hindbrain development, right? So what we really have as our tool, as our real scientific data, generally is structure, and the structure in the code of scientific models, right? These are the things that we're able to get. These are the things that we're able to verify. And so the real question becomes, how can you use scientific models as your data within a machine learning type of framework, right? How can you use this to augment the data that you can get? So scientific machine learning is domain modeling integrated with machine learning. You're not trying to replace everything with a neural network. You're trying to say, this is a large source of data that I have. This is something that's been verified over many years. How do I utilize known physical equations or known biological interactions with the neural network? So that way the neural network has to learn less, and it can be physically constrained such that, you know, by definition or by choice, it's only going to give you physically realizable outputs. So to really understand how to build such a kind of system or how to work with these kinds of systems, let's really start pulling these models apart, right? So it really comes down to a dichotomy between mechanistic models and non-mechanistic models, because there's two basic ways to model, right? So a model is actually just a nonlinear function, which just says if you have a number, then it spits out a new number, right? So if you have the number of rabbits today, your model is going to tell you how many models you expect to have tomorrow. And there's two real ways that we're doing this, right? So differential equations or other scientific simulations, these describe mechanisms and structure that let the equations naturally evolve from this description, right? So we saw this in the ecological models where we say, here's a mechanistic assumption that the number of rabbits increases proportionally with the number of current rabbits. Right, and so you can have these mechanisms. You can have these first order interactions between chemicals that you know are interacting with each other. Right, you can have your first order physics relationships in there, and then you say, if all these relationships are true, what should I be expecting about the future? Machine learning is kind of taking a very different approach, right? You specify your model as a learnable black box, and you ask the question, what are the parameters that the black box should have such that the input-output relationships are correct? And what a lot of people have been asking these days is, well, which is better, right? Should we just replace everything with machine learning because it is a black box and it can kind of learn to do anything? But that's really not the right way to think about it, right? Because mechanistic models, they understand the structure. They tend to extrapolate beyond the original data fairly well, right? So, you know, a lot of examples in physics, like gravitational laws, they don't extrapolate perfectly outside of the original data sets, but you can get surprisingly good estimates for how a galaxy should work by understanding gravity on the solar system, right? Which is not something you expect a neural network to be able to do. And these mechanistic models are interpretable, right? You can sit there and you can understand all the terms in there, and you can ask questions of, if I was to add this new mechanism, what would happen? But mechanistic models are limiting, right? Because by definition, in order to have a mechanistic model, you have to know what the mechanism is. And I think that in the case of epidemics, like in, you know, COVID-19, a lot of people will sit down and say, you know, the SCIR model is missing a lot of the mechanisms, and therefore it's not able to do a lot of great predictions, right? Or maybe it's too naive, and, you know, all these little details where if you don't know the actual mechanism, then you might not necessarily get great predictions. And so finding out what the mechanisms are, it really becomes the core of mechanistic modeling, and that's the hard part. And non-mechanistic modeling is able to get completely around that, because these models, non-mechanistic models, when trained against data, can be very predictive without having to specify or interpret what those mechanisms are. So neither is really better. They just have very different strengths and weaknesses, right? If you know a lot about mechanism, it can be very enlightening to include that, and it can be very helpful for extrapolation to include that. But there are, in a lot of cases, you don't actually know all the mechanisms, and so you need to be able to incorporate data in a smart way. So this leads us to mixing the two, right? So what we want to do is we want to add scientific structure to our machine learning to be able to use the two in tandem. And so how can we do that? Well, the key idea behind this is to utilize the universal approximation theorem. So the universal approximation theorem is that neural networks can get epsilon close to any Rn to Rm function. So essentially what that means is that a neural network is this weird object where if you literally just make a neural network large enough, what it really is mathematically is it's this Rn to Rm function, right? So it's a number, it's something that takes in n digits and it spits out m digits. And if you get the parameters right, it can match any possible function from n things to m things, right? So it's, if you know about like things like Taylor expansions, you know, Taylor series can approximate any possible function of a certain class, right? Which is a pretty large class. In some sense, you can say that, you know, well, you can always write down a polynomial. If you pick the right coefficients, then it'll match the function close enough, right? That's essentially what a neural network is, because the universal approximation theorem. So what you can do then is you can say, well, neural networks are really just a way to be able to perform nonlinear function approximation, right? So if you had the function e to the x, you can write it out in a polynomial basis and find what the coefficients are. You can find special nonlinear forms, and you can ask the question, what are the values a in this model? But in general, matching a nonlinear form can be quite difficult because it needs to be kind of structured to your equations or to what you're trying to match. But a neural network is one that's literally, here I write it down. You have an input x, you do a matrix multiplication, you add a vector, you do some nonlinearity, so that's what sigma stands for. Then you do another matrix multiplication, add a vector, nonlinearity. Each time you do that process, that's just called another layer. And what you can prove about neural networks is that if you make those layers large enough, so if you make the W matrices shaped such that they have enough rows and small for the columns that you have, then it can get epsilon close to any possible function. So you don't have to choose a specific nonlinear form anymore, right? The purpose of a neural network is it's a nonlinear form for approximating any possible function. Yeah, so I mean, you can also think about using some other things like Fourier and Chebyshev series, right? You can prove that any continuous function can be represented in 1D, can be represented by a Fourier series, and then you can take tensor products of Fourier series to be able to build up high-dimensional functional approximators. So why do neural networks get involved, right? Why should we be thinking about neural networks in this sense? The reason is because neural networks are universal approximators that work well in high dimensions. This is what we call overcoming the curse of dimensionality. The way that this is rigorously described is that normally, if you're to use a classical function approximation method, the amount of parameters that you need when you increase the dimensionality increases exponentially, right? So if you think about doing something like a Fourier basis in high dimensions, you do like sine of x times cosine of y, and then you do sine of 2x times cosine of y. You'd have to do every single combination of x and y. And then if you do 3 dimensions, you have to do every combination of x, y, and z. If you're to use tensor products or these other kinds of bases, the number of basis elements that you get as dimension increases grows exponentially because you're doing combinations. Neural networks have this property where they can approximate high dimensional objects with polynomial numbers of dimensions. And so the idea of doing an Rn to Rm function, something that is in very high dimensions, is something that's very simple to work with a neural network, right? So that is why neural networks have really caught on for this kind of data-driven modeling. They are a high-dimensional version of a black box. A neural network can literally be something that can approximate any possible function, which is both a pro and a con, right? Because it means that you can use it as your entire model, right? You can literally say, I have an input-output relationship. I don't know what to do about it. I'm going to make my neural network be that input-output relationship, and is going to train it on the data that I have, right? So it can approximate everything. But because it can approximate everything, it means that it's very good at learning exactly what you want, learning exactly what the data set wants it to be. And it means that the moment that you leave the data set, well, it can do any possible behavior, right? It's not constrained to be, physically reasonable or, have the right asymptotics or anything. It can literally do anything. And this is why neural networks training requires big data and lots of compute time, right? Because you have to make sure that you really make sure that the neural network trains to do the thing that you want it to, which it might not necessarily be easy to do because it can literally do everything. So this is really the pros and cons that everyone in machine learning is really trying to always deal with. So now let's get back to the scientific aspect, right? So we know that neural networks are something that can approximate everything, but we want to be able to add structure to them so that way they can only approximate things that are scientifically reasonable. We have the structure of science being things like differential equations. Let's use neural networks inside of differential equations to be able to constrain it to only give physically realizable outputs. So this is where we get to universal differential equations. So universal differential equations are neural networks that are literally put inside of differential equation models and are trained within the context of that model. So what this actually looks like is here we have a system where it's U prime equals neural network, And the neural network is then spitting out values for what it thinks the derivatives are. Numerical differential equation solvers and then ran over that. And then that gives you what a trajectory is. And how this is working is that it's backpropagating through the ordinary differential equation, through the neural network with inside of the ordinary differential equation, to then give a guess of, if this is the neural network parameters, this is what the ODE will output. Let's update the neural network parameters, and then let's get a new output. And what it's going to do is going to train the neural network with inside of the ordinary differential equation model until it's able to match the data, right? So in this case, what it's doing is basically saying, I believe that the time series comes from a differential equation model. Find a neural network that represents the function for that differential equation. And it'll run this process, and it'll give you out the differential equation after it does its training process. So how well does this work? How well does trying to learn a full model from scratch work in practice if you're trying to just learn the differential equation? It doesn't work all that well, but what you can do is you can change this to be able to learn smaller and smaller bits. So for this, what we did for this demonstration, right? So this is not going to be the full example that I'm talking about, but this is a nice constrained demonstration. Or what I'll do is I'll try to perform some model discovery on some data that comes from the Wuhan region of China. So if you're to try to train a neural ordinary differential equation, what you're basically saying is U prime equals a neural network based on U, right? So given my current state of the number of infected people, the number of people in the hospital and all this, you can just say this is some differential equation, learn what that differential equation is. And what I did here is I trained the neural ordinary differential equation from day 0 to 21 on that data, and then I just let it run longer. And what you can see is that it doesn't extrapolate well, right? It actually extrapolates a lot better than if you're just to do a pure neural network, but it doesn't really capture the asymptotic properties that you would expect in an epidemic model, right? But the key here is that we know more than just we know more than just the fact that the structure to this item is that it's time varying, that it's growing over time, right? What we know is we know a lot about how epidemics should be working, right? So we have a lot of information on, well, the rate at which people recover from the disease is kind of fixed, right? Because that's a disease parameter that people know. So you can have parts of an SEIR model, or here's an extended SEIR model, where you can write down a lot of these terms and get pretty good guesses, right? But the thing that's really hard to know is how often are people exposed to the disease, right? This is really the core uncertainty in our models. And what we can do here is we can say, well, if this is a portion of the model that's unknown, let's replace the unknown portion of the model with a neural network, right? So we can stick a neural network here, and we know by the mechanism that whatever we're taking out of these susceptible people are going to become exposed. So this is our exposure relationship. We can put a neural network in here, and then we can train it to match the data from 0 to 21 days, right? And what happens, what you see is that now that we've encoded a bit more structure in the model, right, it's able to learn how to work from 0 to 21, and then it's able to extrapolate quite a bit better after the first 21 days. Right? Because it's what we've done then is we've constrained it to be able to have behaviors that are really representative of epidemic models. And we're just saying, learn something that we know that we know in our original model was probably incorrect. Right? Learn something better for what is the very uncertain piece of the model. So one thing that we can do next is then we can try to interpret what the neural networks are doing, right? So one thing that people have gone to is, well, can I just take data and be able to find differential equations from it? And the way that you can do this is you can create a matrix of your observables and a matrix of your derivative data, and then you can turn this into a linear approximation problem. And then you can find a sparse space. You can find coefficients for a sparse basis that represents your differential equation. If you're to do these kinds of sparse identification on something like a epidemic model, well, you have exponential growth, which means you have exponential errors. And so these processes don't work very well, right? So this is what if you're to run an SEIR and then ask it, well, perform the model discovery on this and tell me what you think the leading terms are, this is what you get out of it, which is not fairly nice. But what we can do is we can take this idea of sparsification back down to real equations and use that to be able to answer the question of what are the mechanisms that the neural network is finding, right? So what we do is we take this unknown portion, this neural network that we trained in here, and then we return this neural network into real mechanistic equations, right? And then what we see is that when we do this, we have a sparse model which has new mechanisms, right? So these mechanisms are, we have a term for exposure that's based on the number of susceptible people, one that's based on the number of susceptible people times the number of infected people, and then susceptible people squared times infected people from a huge basis. And one interesting thing is it says that D, which was the number of people who were who received the disease but ended up having to be hospitalized. The number of hospitalizations essentially does not affect the number of people who ended up exposed, which you can then interpret what that might mean. But after we then replace this neural network with a sparsified form that matches what the neural network was doing from 0 to 20, what we can do is we can then extrapolate with the sparsified model, and you can see now that it gets fairly correct, right? So we're still only training from 0 to 21. We're now just using a sparsified form of what we trained to be able to extrapolate in the future. And because it seems to be picking up some realistic mechanisms, it's able to then extrapolate beyond the data set quite well, right? Because it's understanding things like, well, people who are hospitalized don't tend to be the ones exposing people to the disease, right? So even though we allowed the neural network to learn a relationship there, the neural network says, oh, that's not a significant effect. And it learns that, here are the mechanisms that you were missing. And those mechanisms, if you're to look at them, right, they're based on I and they're based on S in a way that will have the right asymptotics for an epidemic model. So by using this approach, we can augment known models with data-driven components and then be able to use them to recover the missing mechanisms in the model. So this is not so this is kind of magical the first time you see it, because we only trained it here. And then you say, what happens in the future? And it got it correct. But this is not the only case where this has worked out. This seems to be working out in a lot of cases. And one case that we've been looking at, for example, is in ecological models, where in this case we said all that we know in the ecological model is the number of rabbits grows exponentially, the number of wolves dies off exponentially, find the other pieces. And when we perform the same idea, right, so we train neural networks to be the missing parts of the model against data, then it learns to work well with the data. We sparsify it down to equations. What you can see is, even though this does not see anything about the future, it just sees a drop in the number of a drop in the number of wolves and a rise in the number of rabbits. It's able to extrapolate to the future and understand that it's going to be cyclic in the future, given the structure of the missing scientific equations. Right? So this is really the key then, that we're not using neural networks. We're not using neural networks to try to solve the whole problem. We're trying to use neural networks to augment the existing knowledge that we know, so that way we can utilize all of our previous knowledge and then be able to utilize a much more constrained neural network, because when neural networks run rampant, then they can do weird things, right? And what we get out of this as well is we can discover mechanisms, right? Because we're back to mechanistic models. We go back to, hey, here's a neural network in a model. What are the equations that you find? Well, you found quadratic interactions. You find these interactions inside of the SDIR model, and you find that there are some interactions that don't exist, right? So you get back to something that's more interpretable, and then something that you can start to play around with simulations and do bifurcation theory, because we're really using the neural networks as a step back to mechanisms. So how is this being used within the context of COVID-19? Well, we're using this to be able to do two things. One, be able to develop new diagnostic tools, and then secondly, to be able to identify new approaches for mitigating disease spread. So one of the things that we've been doing here, this paper that will be submitted soon, is that we're using it to identify and quantify quarantine strength. So we have one of these SIR models with a pool of people who are which have the disease but which are not showing symptoms. And what we do is we say, well, what people usually have as this term in the SIR is really, should be a function of quarantine strength. So this quarantine strength is then something that we estimate by making this into a neural network, right? And we train this neural network against the data such that we have this SIR model with the neural component in here. And then what we did was we looked at how does this quarantine strength actually act. And if you actually look at some of the states, for example, in the United States, you'll see it gives you results that you would expect. So for example, in California, we saw that, you know, a few days after after the quarantines were imposed, we see that the quarantine strength that is learned through this neural augmented model ends up increasing. Right, so this green line and red line are actually right on the dot, and you can see that they're all, you know, kind of right next to each other. So what we can do now is we can say we can go from time series data with SIR assumptions to be able to use that to back out what ended up being the quarantine strength. How would a quarantine actually work in given areas? And this actually leads to interesting trends. So we're able to find, for example, that in a lot of cases, you can have highly efficient quarantines that, that correlate to certain governments. And then you have certain governments which were not able to really have, you know, effective quarantines. And it corresponds to the governments that you would believe have done well or not have done well with this disease, right? And what this means then is, you know, we can double check that this thing is working against a few countries, but now we can run this en masse. So we're using this diagnostics now to be able to use this against all the country statistics and then be able to say, you know, what are the countries that have had effective quarantines and which ones have not had effective quarantines. And now that we've reduced time series information to quarantine efficiency, what can we learn about the set of countries that end up having effective quarantines and which ones did not have effective quarantines, right? So we're transforming the data now into something that is much more usable for understanding the effects of policy decisions. So beyond diagnostics, though, can we use scientific machine learning to inform new mitigation techniques, right? Because this is really what we want to understand. We want to answer the question of, you know, can scientific machine learning tell us what days we can go outside such that we get rid of the disease, right? The real key to this that we found, though, is this second question, which is, can we extract meaningful information, for population level information, from cheaper and simpler data sources, right? Because the difficulty with what's going on right now with COVID-19 is that getting accurate data is just extremely expensive, right? You could say that we can do widespread testing, and some people in the United States government have said that everyone who wants a test can get a test, but we do know that that is pretty much infeasible, right? It's also expensive. And so right now there's been a lot of test rationing, and so we don't really have an accurate count all the time of everyone who has had the disease because testing just can't happen en masse like we would want it to. Right, so one of the ways that people have been shifting then to be able to try to understand who might be getting infected is through contact tracing. Right, so Google, Apple, and many governments around the world have been looking at whether contact tracing can be an answer. And the difficulty is this requires really high coverage to be able to be indicative of population level statistics. Right, contact tracing is really good for, you know, it works well if you know one person is infected, then you can know who they might have infected, but it doesn't really answer the question how many people are infected unless you knew a lot of the people who are infected already, which would again require that you've had widespread testing, and so it's not necessarily something that you can get to. So the other thing that really comes up is that contact tracing works in a biased subset of populations, right? So we like to say that technology is unbiased, but in this case, this is definitely a case where technology is biased because, well, those who have access to healthcare, which is something based on age and ethnicity and, you know, social class and these kinds of things, those people will have a much higher chance of actually being able to attain a test or be able to get the proper healthcare. And those are also the people who will generally have better smartphones to be able to install the apps. And so people in a position of privilege will more likely be able to be found having, you know, the disease through contact tracing than people in other areas. And so what this means is that we're actually not getting a good, through contact tracing, we'll get good information, right? It'll solve a lot of issues, but it won't solve the issue of how many people are infected. And what it will definitely undercount it will undercount, you know, communities of color and communities with lower access to healthcare, which we really need to use to understand how the disease is really spreading, right? And so what we've been, the general idea that that we found through our scientific machine learning. Before I get to the results, I kind of want to just summarize it a little bit with one high-level slide, and it's that the law of large numbers means that useless tests are actually useful, right? So to really wrap your head around how to make use of a useless test, let's look at some statistics that people use for learning about the base rate fallacy with breast cancer, right? So with breast cancer, about 2.4% of women develop breast cancer, and a mammogram has a sensitivity of 87%, and it has a false positive rate of 12%. And so if you know the base rate fallacy, what you can essentially do is you can say, well, if I had 10,000 people, with 2.4% get cancer, then, I can split it up here. If this is my sensitivity and my false positive rate, you can split it up. And if you actually just count the number of real hits versus the number of false hits, what you can find is that you have about a 15% chance of actually having cancer if a test comes up positive, right? So this is what people call the base rate fallacy, because there is such a low chance of actually having the disease if the test is true. It's much lower than you would probably expect. And what it really implies is that, if you have a test that has 90% sensitivity, it's still going to give you so many false positives that you really don't have a clue who has the disease still. And so this really is used to show that, inaccurate tests, even at the level of 90% sensitivity or, 10% false positive rates, are so inaccurate that they can actually be a bit dangerous if you're to use them to try to understand who has the disease, right? But we can completely change the question that we're asking in order to get something useful out of this, right? So if we roughly know the sensitivity and the false positive rate, can we estimate the rate of the disease, right? The number of people who have the disease. So if you have a good sense of how bad your test is, you can basically run this in reverse. You can say, well, if I know the percentage of people who have, if I know the sensitivity, then I can get back to the number of people who probably had it from this group. If I knew the false positive rate, I can probably get the number of people who had it. And therefore I can get the percentage of people who had the disease, even though I cannot trust the result of any single test on a given person. And what this really means is that, we know this as the law of large numbers, that averages tend to work, right? So even though you don't necessarily know if any single person has the disease through a bad test, the overall percentages that you get from bad tests run in mass still gives you a good population average, right? And so this is really what we're seeing as the result from our scientific machine learning simulations that we've been doing. So let's take this idea from theory to reality and look at two of the different cases that we've been doing, two of these different scientific projects. So one has been with the Alan Turing Institute, which is COEXIST, which is literally looking at this topic. So it's looking at COVID exit strategies in the United Kingdom through cheap testing with easy access. So, right, so what we do in this case is we assume that we're able to get millions of tests out to people, but we aren't paying for very accurate tests. We're just paying for the cheapest tests that we can have. And what we see in these simulations is that tests with only a 60% sensitivity, or even 50% sensitivity, are perfectly fine for us to be able to understand which regions of the United Kingdom have more prevalence of the disease, and be able to do region by region levels of quarantine to be able to reduce the time that to be able to suppress the second wave. And what we see in these simulation strategies, which is stratified by it's stratified by age, it's stratified by different regions. But what we see in this complex simulation is that what matters more is that the number of daily tests that are carried out, and not really their sensitivity. Because if we have a general idea of how things are changing over time, it doesn't matter if it's only catching 20% of the cases, if we know that the 20% that it's capturing is a number that's going up, right? So what this means is that we don't really have to, it gives us a possible strategy that is, well, what we can do is we can utilize cheap tests and just give them out in mass as a way to then be able to understand how things are changing, and utilize that to be able to do much more informed policy decisions. The other thing that we've been working on, so this has been in tandem with Cornell University, University of Queensland, and University of Melbourne, is we've been developing a system called SafeBlues, where SafeBlues, what it's doing is it might sound a bit like contact tracing at first, but it's actually quite different, right? So what we do is we have this app on the, we have these apps that everyone has installed. And then when you're nearby someone, there's a chance that you'll be able to give the person next to you the strain, right? These parameters for how the strains work, the infectivity and all these can be different by strain. Right, so what we can do is you can run this essentially virus simulation, which is contact-based virus simulation, have thousands of different strains or strands going on at the same time, and this can serve as a proxy to understand social structures and quarantine effects, right? Because if it's using the information of who's nearby who, then it's gathering, in some sense, it's almost capturing this information of, what are the social structures? When do you have someone from this social structure move to another social structure to be the cause of a, what's the word again? To be the cause of a super spreader event, right? So it's capturing a lot of these information without actually having to understand who is infected. And so what we did with this information was, we're still in the development of this app, but what we've been doing is we've been looking at simulations to say, if we were to create this kind of app, can we pull meaningful real-time information out to be able to inform policy decisions? And so what we did on some simulations was we showed that if we had 100 days worth of this SafeBlues data, then what we can do is we can utilize a neural network that trains between these different strands, right? So some strands will be more infective, some strands will be less infective, but we can learn an aggregate of the strands that basically matches what we would expect for the number of infected people on the data that we already have. So the data that is of the past. And then when we're in the future, right? There's like about a 2-week lag before you get actually good estimates for the number of infected persons. What you can do is, if you were to look at the SafeBlues estimates in this time, in real time, and then we backtrack afterwards and say, well, what did it end up actually being? What we see is that the SafeBlues that's trained to understand how these different strands are working is able to then predict in real time what the infected statistics will be when they finally update. And the reason for this is really because it's capturing all the information it needs, right? Because SafeBlues is then something that is well correlated with how the disease spreads. And so then as long as you can train something to match, how these fake diseases are spreading to match then the real disease spread, when you have people who are interacting more, then suddenly SafeBlues goes up and you would expect the real number of diseases to go up, right? And so what we've been able to do then is we've been able to utilize many different models. So we have, if you look at our paper, there's it goes from simple SIRs to larger agent-based models, showing that this idea of having these fake diseases with full information running at the same time as a real disease, it gives you diagnostic information that you can actually use and correlate back to the real disease. And what we're then able to do there is we're able to utilize scientific machine learning and say, well, if we were to understand, can we then relate how policy, right, measured through the SafeBlues parameters and measured through the amount of contact and things that we see, can we then pull this back to be able to understand what is actually necessary to be able to get R0 below 1, right? And so then we're able to train these neural networks within SIR models utilizing the SafeBlues information, and then being able to identify, oh, at this point in time, we were able to get, this is where R0 ends up getting below 1. And we're able to then pinpoint what points in time in the past corresponded to that to be able to then understand this is around the amount of policy that we need, or this is the amount of restrictions that we need to be able to get mitigation of the disease. So the strategies of COEXIST and SafeBlues, what we're seeing is that they're basically using these ideas of scientific machine learning to be able to transform the problem of how to do precision policy making into one that's data driven. And so the secondary thing that we've been having to solve then is, well, if we're trying to use scientific machine learning everywhere, right, we're putting neural networks into things that were once just simple differential equations or simple agent-based models. Now you have an agent-based model with a neural network. You can guess that this thing is going to be very difficult to computationally handle, right? So the next thing that we really need is tools for real-time scientific machine learning. So this computational aspect is where a lot of the rest of my research has gone. And so the interesting thing that you can do here, though, is that You don't need to just use neural networks to be able to augment and make better models. You can also use it to find smaller models that give approximate information to be able to accelerate your simulations. So one case where we've shown that this works quite well is actually in climate modeling. So in climate models, what you have is you have the three-dimensional partial differential equations for the Boston-esque equations. And what you can do then is you can take this integral in the XY domain. Right? There's a bunch of technical information how you get here, but you can basically say that there is a one-dimensional partial differential equation that approximates the original three-dimensional partial differential equation. And it's a great approximation, except for the fact that you don't know what this function is. This function itself is defined by another partial differential equation, which is missing a function that's defined by another one. You actually have an infinite cascade of missing equations. But the same idea can be used here, right? So here's a very expensive equation. Here's a very cheap one, where if you knew this function, then it would approximate this original one. And so what we do is we replace this function by a neural network. We train this neural network within the context of the climate model. And then what we're able to do is we're able to replace the expensive equations with the much cheaper equations. I mean, here we actually get a 15,000x acceleration over the original 3D PDE form, because I mean, if you know your computational science, we just replace the 3D PDE by a one-dimensional PDE that approximates it extremely well to the point where you can't even really see the data anymore. The predictions are right on top. So you don't need to use this technique just as something to be able to augment existing models. You can also use this as a way to be able to find approximating models, to be able to simplify your models. And so we showed this also in the case of non-Newtonian fluid simulations, where we take these original differential algebraic equations, we find approximating nonlinear forms to them. And here, once again, we're able to do this kind of acceleration process by finding smaller models that get very close to the original model, but capture the same, but still have to satisfy physical relationships. Another thing that we've been finding out is that you can utilize neural networks wrapped around physical simulators to be able to turn them into real-time prediction pieces. So the way I like to explain this is through the Lotka-Volterra equations once again. So here's just a really easy example, right? So we have a model of rabbits and wolves, and there's 4 parameters in here, and we ask the question of, given a value of alpha and beta, can you tell me a gamma, a delta and gamma, such that the solution stays within 0 to 6, right? So that would be a very, you can sit down at your computer, you can say, well, you give me alpha and beta, and I'll punch in a bunch of numbers and see which one ends up working in here. But what we want to do is we want to do this automatic, and we want to do this automatic in a way that a cell phone can give you a result in real time, because these are the kinds of things that we'll need to solve if we want to do this automated data-driven policy decision, right? And what you can do then is you can train a neural network as the nonlinear function that is exactly the problem, right? So you can have this neural network be, I take in alpha and beta, I spit out gamma and delta, and this is now a neural network that goes directly from what did you give me here to, if you fiddled around with the values, what is a value that would be between 0 and 6, right? So that is itself a nonlinear function. So you make the neural network be that nonlinear function and have your cost be, well, if I was to put in these 4 values, or these 4 values of the parameters, do I actually get something that's within 0 to 6, right? So that's now just a classification problem. And so the same way that you train an image classifier, you use this to train something that can classify whether the predicted to other parameters is something that will give you this result from the differential equation given 2 known parameters. And it turns out that, when you do this on a simulation, the nice thing of doing this on a simulator is you have infinite data. So here we can start from Lotka-Volterra equations, and we can train it once and see that, in the first case, you have one case that is able to give you a bad piece of data. And then you say, well, I have full control over this model. So if there's a point in there where alpha beta to delta gamma is giving me bad results, well, let me just train in that area which had bad results, and you can keep on adapting your simulation until it's essentially 100% correct, right? And what we then have is you no longer have to use the full simulation to be able to understand how you can do the control. You can just ask the network for the results of the control without running simulations. And then this gives you a way to be able to go directly to results without having to do something that could be expensive, right? And so then what we did was we looked at doing this on the Gierer-Meinhardt equations, where, you know, this is a two-dimensional partial differential equation. So this is something that can take minutes to solve. And what we were able to do is we were able to train a neural network in a similar way where it takes in 3 parameters and it spits out the 3 parameters that you'd need to have such that you have non-homogeneous results. So for a lot of parameters, this gives you a result where the value of the concentrations are always the same. There are some parameters such that it gives you spots. And we trained a neural network such that, you know, you've taken some of these parameters and it'll instantly give you out what parameters you need to put in such that you would get spots. You know, it's able to do this on the order of microseconds, even though a simulation to be able to check whether the solution is true or false can take minutes. Right? So you can use neural networks around these scientific simulators to be able to turn a result of a scientific simulation or, you know, optimization over scientific simulations into something that is now real time. So you can disconnect the complexity of the simulator and its computational cost from the ability to be able to utilize it real time, in real time in an automated way. And so what we're doing, what we're really seeing is that scientific machine learning does require the efficient training of universal differential equations and these other methods of scientific machine learning. And we've been building up a package ecosystem in the Julia programming language to make this easy and efficient. So diffeqflux.jl, for example, is what I've been showing a lot of. It's part of the SciML organization in Julia, where all these different universal differential equations, like, you know, you take differential equations, you use the neural network library to be able to stick neural networks in there, and then you tell it to train it, and this whole process is automatic and the whole process is automatic and optimized. And then if you're someone who is a differential equations or computational science wizard, I have this slide in here so that way you can know that it can be applied to real problems, right? So for a lot of those climate modeling examples, we've been doing, you know, batching on GPUs with high order adaptive implicit methods for stiff equations with matrix-free Newton-Krylov, preconditioning GMRes, checkpointed adjoints, all the details that you'd want from a scientific simulator are able to be used with neural networks imposed in all these different steps. And so we've been using these for, you know, neural networks to be able to derive preconditioners and all sorts of different things that would be required for large scale, you know, climate science type problems. So this is not something that's at a toy stage, right? This is something that's really at a real application stage. If you want to see some tutorials on this, we have a tutorial out that goes into some details on things like how you can do automated sparsity detection, preconditioning, matrix coloring, and all these kinds of details. Follow that link, or if you just search for Julia differential equations, all this stuff should come up. So has this accelerated real applications? The answer is very much yes. I'm going to be running out of time, but what I'm going to do is at least just mention a few numbers on how this has impacted some of the work we've done. So with the Microsoft pandemic response, we partner with Microsoft and GitHub to be able to host some of these models for like the COEXIST model and other models that have been being used. And as part of this work, what we found was that we've translated some models from Python over to Julia, and we've utilized these scientific machine learning techniques, a lot of them automatic. And what we've seen, for example, is the COEXIST model ended up accelerating by 36,000 times when we performed this change over to Julia, and we received automated parallelization when we did this. So we're now at the stage of, you know, we're trying to get this in real time to be able to do monitoring of all the different regions of the United Kingdom. And this 36,000 acceleration has really helped, because before we thought it was going to be a full cloud level problem, but now this might be something we can do with, you know, 1 or 2 compute nodes. We're also using scientific machine learning to be able to accelerate clinical trials. Right, so I mentioned at the very beginning that I'm scientific director of this new Pumas AI startup, and I have a position in pharmacometrics in the University of Maryland. Sadly, there will definitely not be enough time for all that in the talk, so I made sure to put in one slide here that basically goes over what we've done is we're using these techniques to be able to approximate, to be able to understand what are the missing parts of these models in quantitative systems pharmacology. So when you have multiple drugs being used at the same time, how can you automatically figure out what drugs are interacting and which drugs are not interacting from the data to be able to then predict whether future clinical trials will succeed? And what we've shown is that, you know, this methodology is useful, And B, when you apply these new tools that we've developed, we've been able to accelerate the models that people are using inside of Pfizer by about 8 times to 170 times over their previously heavily optimized C code. So they have had these codes for a very long time, very heavily optimized, but with these new tools and these new forms of simulation, especially with these neural network augmentations, we've been able to get about 175 times faster, which is now increasing or decreasing the time it takes to go for full clinical trials to run. A lot of this still is in development, but the things that can be said is that there's some companies in, for example, the Cambridge area that are working on mRNA vaccines for COVID-19, and those clinical trials are utilizing PUMAS and its accelerations to be able to get this through the FDA. So there will be a lot more information coming out on that in the future, and that's about all I can mention on that right now. But if you want more details on exactly how we've been accelerating these pharmacometric simulations, I'll be giving a talk in about 3 or 4 weeks on automatic optimization and parallelism in differential equations.jl. And that'll go into a lot more details about what are the ways that we've been automatically parallelizing and fixing up people's code, such that people can now give us bad, in quotes, bad code, and we can just simulate it fast anyways. So in conclusion, really machine learning can be improved by utilizing scientific knowledge in numerical analysis, right? So machine learning is not something that we should really think about as, we have machine learning and we have mechanistic modeling, and these two camps should never talk to each other. We should really break down that barrier, right? Machine learning with scientific knowledge are these neural differential equations, and they seem to be very useful for diagnosing what's going on with COVID-19, for coming up with new treatment strategies, or even just for accelerating previous scientific models. And what we've seen is that the composability of these Julia tools has really made this training possible, and it's really democratized the process. We're now gotten from the point of, you no longer have to be a specialist to be able to utilize all these things. You can just stick neural networks within existing scientific models and then start to ask the question of, were the missing pieces to my model? Will this accelerate my model? And all these other things that we've been doing with scientific machine learning is now something that, you can get an undergraduate to start trying out these ideas. So thank you very much. Thanks for having me. And thanks for letting me share my work here.